Hello and welcome to this presentation on understanding HF propagation. I'm Steve Nichols, G0KYA of the RSGB Propagation Studies Committee. In this presentation we're going to look at the sun, sunspots and their effect on HF propagation here on Earth. We'll also look at how conditions can change from day to day and month to month and how you can make the best of it. We'll also look at how you can use HF propagation prediction programs to work out the best times to work from one part of the world to another. Well, with that out of the way, let's move on straight away to the next slide. Now the sun, which is our nearest star, is a massive ball of hydrogen that's going through a process of nuclear fusion to turn it into helium, and in doing so it emits a massive amount of energy. We're particularly interested in the electromagnetic ionizing radiation that comes off from the sun. That's the ultraviolet and soft X-rays. Now, put simplistically, the more sunspots there are on the sun, the more ionization we get on Earth, or the more sunspots there are, the greater the ultraviolet output from the sun, which then causes ionization here on Earth. Now, how do we measure this? Well, it'd be very hard to actually measure the ultraviolet output of the sun actually on the Earth, because the ozone layer actually blocks an awful lot of it. Scientists found that there was another way of doing it, and that was to measure the radio output of the sun at a frequency of 2.8 gigahertz. That's a wavelength of 10.7 centimeters, and this gives us something called the solar flux index, or SFI figure. And there's a strong correlation between that SFI figure and the amount of ionizing radiation coming off the sun. Just to be clear, it's not the radiation at 2.8 gigahertz that ionizes our atmosphere. It's actually the ultraviolet output, and we just find there's a strong correlation between the 2.8 gigahertz output and the UV output, so that's the figure that we can use. The solar flux index can be as low as 65, as it was in 2008, or as high as 274. Which we saw in 2001. It can even go up to around about 300. At the moment it's been about 70, but that's because we're at the bottom of solar cycle 24. The current predictions are that the minimum will be somewhere between April 2020 and October 2020. When solar cycle 25 does start, and there are signs that it is coming, we can expect the solar flux index to rise quite quickly. Now, another way of working out the solar output is to actually count the sunspots. And for this, we have something called a sunspot number. But very quickly, a sunspot number doesn't mean, if we said there was a sunspot number of 98, that doesn't mean there are actually 98 sunspots on the sun at this particular time. If we use the Wolf sunspot number formula, you basically get 10 points for every sunspot group that there is on the sun and 1 point for every sunspot. So if you had one sunspot on the sun, you'd have one group, so that's 10, plus the one sunspot that's in that group, so the sunspot number would be 11. Likewise, if you had two sunspots in two separate groups, that's two separate groups, that's 20, plus the two sunspot numbers, another 2, so that's 22. So as I said, it doesn't actually mean when you hear there's a sunspot number of 98, that there are actually 98 sunspots on the sun, but this is the way that we can actually work out a number that we can use generally. Now, on a day-to-day basis, the overall sunspot number and solar flux index can change quite rapidly. So to smooth things out, if you like, we have a smooth or average sunspot number. That's what we use. We call it a smooth sunspot number, which is a moving average, if you like, over the past few months of sunspot data, and gives us a figure that we can then use with our propagation prediction programs like VOACAP, VOAPROP, HAMCAP, and the rest. So this smooth sunspot number is actually very, very useful when we're using propagation prediction programs. Now, as I said earlier, the solar flux index can vary dramatically over the 11-year sunspot cycle, and this has a drastic effect on the maximum usable frequencies we can use on any contact across the globe. For instance, here we've got two plots. The lower green one shows a maximum usable frequency plot on a solar flux index level of about 65, which is the kind of thing you'd find at sunspot minimum. And as you can see, on a path from London to perhaps New York in October, you'd be lucky if you could use up to perhaps 18 megahertz. But then again, the yellow plot shows us another prediction with the solar flux index at 275. So that's the kind of thing you'd find at sunspot maximum. And it shows you that the maximum usable frequency is way above 30 megahertz. So it's at solar maximum that we find that 10 meters really comes alive. That's 28 megahertz. And you can work the world with very low power on 10 meters. Where at solar minimum, you may struggle to hear anything on 10 meters at all, apart from in the summer periods when we get sporadic E, which isn't really solar related. Now, in addition to having sunspots on the sun, we also get other phenomena, and one of them that can be a bit detrimental to HF propagation are solar flares. Now, these are connected with sunspots, and these can be quite devastating for the HF bands. With a sunspot, you have twisted magnetic fields, really. They're really tortured and wound up. And eventually something has to give, and they do. And when that happens, you get a massive output of ultraviolet and X-ray radiation from these solar flares, which then flows out to the Earth at speed of light. So in 8.5 minutes, it reaches the Earth. And once it hits the Earth, this radiation can cause massive D-layer absorption and give us poor conditions on the HF bands, especially on the lower bands. Now, these solar flares are classed according to their severity, and the most powerful ones are X-class solar flares. And we can measure the intensity of these flares, if you like, with satellites. And as I said, they're classed as A, B, C, M or X-class flares, with the X-class ones being the most violent of the lot. And within each X-ray class category, they're divided up into a logarithmic scale from 1 to 9. So therefore an X2 class flare is twice as powerful as an X1 flare, which again in turn is 4 times more powerful than an M5 flare. So if you hear any discussion about solar flares, they're usually given a category or letter category, and it's the X-class flares that are the worst. Now, this diagram shows you the kind of effect you might get from a solar flare. As I said, it hits the Earth within about 8.5 to 9 minutes because it's electromagnetic radiation, penetrates deep into the D layer. Therefore, what we get is that the lower frequencies are quite seriously affected, and say 3.5 megahertz, 5 megahertz can be knocked out completely, and you lose all propagation via the E layer and F layer. But it recovers again within about an hour. But as you go up in frequency, maybe to 10 megahertz, or in this case 20 megahertz, because there's less D-layer absorption at those frequencies, it has less effect. You may see some effect on 20 megahertz, but it recovers reasonably quickly. And by the time you get maybe up to 30 megahertz, the flares don't seem to have much effect at all. But it's not all good news with solar flares, because they're often linked to something called a coronal mass ejection. Now, this is when millions of tons of solar matter, or more correctly plasma, are ejected into space from the site of the CME. And these things are hurled into space at rapid speeds, 1.35 million miles per hour, something like 600 kilometers per second. And so if one of these coronal mass ejections is pointing towards the Earth, then it's going to impact upon the Earth, and we're going to have some effects. As you can see from the diagram there, these things are utterly massive. I mean, compared with the size of the Earth there, which really looks like a pinhead, a CME is quite violent. Now, what you do find as well is that CMEs are more prevalent on the downward portion of a solar cycle. So once you get up to solar maximum and you've got more and more sunspots leads to more and more solar flares, which in turn can lead to coronal mass ejections. So on the downward portion of a solar cycle, these are more prevalent, and you're going to get more and more disruption in the HF band conditions. Now, as we said, so this CME material is hurled off the sun at a rapid rate of knots and can spread out in any direction that it's pointing at. Now, if it's headed towards Earth, if it's pointing in our direction, it's can be channeled towards the poles of the Earth, and we get a condition whereby if the interplanetary magnetic field, that's the magnetic field, this frozen in magnetic field of this CME plasma, is pointing south, it couples more easily into the Earth's magnetic field and is more likely to cause us problems. Now this is called the BZ, or the interplanetary magnetic field. So if this BZ pointing south, this interplanetary magnetic field has field lines that point south, it's more likely to couple with the Earth, and we're more likely to get problems on HF. Now this short animation shows you exactly what happens. So the CME material flies off the Sun at perhaps 500-600 kilometers a second, couples with the Earth's magnetic field and collects in the magnetotail at the back of the Earth. Then, if those magnetic field lines there connect, it can be flung back into the north and south poles of the Earth, where we're going to get aurora. This is what causes the aurora, these charged particles being channeled into the north and south poles of the Earth, where they collide with the atoms in the upper atmosphere, or ionosphere, and they glow, they emit light. So this is how we get the aurora borealis, which is twofold really. On one hand, it can be very good at VHF because you can get aurora type propagation, so you can propagate your signals on 2 meters and 6 meters, but also it can wreak havoc any signal that goes over the North Pole. HF signal, perhaps on 20 meters, is going to be seriously disturbed. So it may be that the signal sounds very, very fluttery, or it may be there is no propagation at all on signals that go over the North Pole. So this is something we have to watch very, very closely. We get CME material hitting the Earth, which can be a few days after a solar flare. It can take 24 to 48 hours for this material to hit the Earth. That can cause some problems with HF, and we may find conditions on HF rapidly deteriorate, get very, very noisy. And as I said, any signals that go over the poles or anywhere near the poles can get very, very fluttery indeed, if in fact you can hear anything at all. Now you can see all this in action at a site called www.solarcycle24.com, where there's a gauge on there from the ACE spacecraft, and it will show you the particle density, it will show you the speed, and also show you the interplanetary magnetic field. Is this BZ pointing south or is it pointing north? So generally, if you have high particle densities, very fast moving CME material, and the BZ is pointing south, all of that is generally bad news for HF, as this material gets channeled towards the poles and causes a disruption on HF. Just to continue this theme, we measure this field strength of the interplanetary magnetic field in nanoteslas. Now that's 10 to the minus 9 teslas. To give you some idea, the Earth's magnetic field is about 50,000 nanoteslas, but the field strength of this interplanetary magnetic field is usually plus or minus 10 nanotesla, so it is quite weak really. And again, to give you some idea of how that compares, an MRI machine, the type of thing you'd find in a hospital, can be 1,000 million nanoteslas, so phenomenal magnetic field in an MRI machine, quite strong magnetic field on the Earth, and a very weak magnetic field in a CME. So just to recap the effects on HF with one of these CMEs, initially sometimes conditions can seem to improve on HF. The maximum usable frequency can actually improve or go up as the CME material first hits. That's usually pretty short-lived. Then we find that the maximum usable frequency can reduce as the F layer is depleted. Now, anything, as I said, that goes over the North Pole or the South Pole, any polar paths will be the worst hit, and this recovery can take a few days. But at the same time, conditions on VHF can improve. We get these auroral conditions, which sound quite strange actually. If you've ever heard a 6 meter or 2 meter auroral signal, it's quite fluttery, quite hissy, sounds like a kind of tea kettle sort of boiling away, if you like. CW can work quite well on 2 meters and 6 meters under auroral conditions, but otherwise sideband can be virtually unintelligible. But also at the same time you get these visible aurora, such as the one in the photograph. This was taken in Iceland in April 2014 when we had a KP index of 3, which is not that severe as a geomagnetic storm, but is enough to show you that it doesn't take much to generate aurora in those regions. Now, just introduced another term there, which was the K index or KP index, which is a measure, a 3-hourly measure of the effect of these particles hitting the geomagnetic field. And it's a logarithmic scale that goes from about 1 to 9 really. And we generally think of auroral conditions as being with a K index of perhaps 4 or 5. So again, the solarham.com or solarcycle24.com website, is both the same website, just different URLs for it, can show you the current K index. So K index of perhaps 1, maybe 2 is relatively settled and means that HF conditions might be good. If you start to see a K index of 4 or 5 or even higher, that's generally a sign that some CME material has hit the Earth and could mean that HF conditions may not be very, very good indeed, but might actually indicate auroral conditions on 6 meters or 2 meters. Now there's two indices that measure this. One is said as the K index, which is a 3-hourly index of conditions. KP is the one you need to be looking for. That's the planetary index for the whole world. We have all these little individual K indices around the world, and they're all brought together into one big KP, K planetary index. That's the one you need to look at. There's also something called the A index, which is an average of these K indices over 24 hours, but it's not logarithmic. So just to confuse you then, we've got the two indices. The K index is a logarithmic one, generally goes from 1 to 9. The A index can go from 1 to 100 or so or more. And that's an average over 24 hours. So you sometimes see a condition where the K index is quite high, maybe 5, but the A index is still very, very low. And this is because the A index is an average over 24 hours and isn't yet really been impacted by the K index going up. And if that happens, usually the next day your A index has actually gone up. So if you really want an indicator of current conditions, the K index is the better one to look at because it shows you the conditions over the last 3 hours, not over the last 24 hours. Coronal holes are another solar feature that can affect HF propagation. These are areas on the Sun's corona with open magnetic field lines that allow solar material to escape. In an extreme ultraviolet or X-ray image of the Sun, like the one on the right, they appear as dark areas. Their effects are similar to that of a coronal mass ejection, but they're not as fast or as vicious, and the effects are generally not as severe. About 2 to 3 days after a coronal hole directly faces the Earth, the solar material from a coronal hole can reach the ionosphere and create a geomagnetic storm with an elevated K index and depressed maximum usable frequencies. Coronal holes may appear at any time of the solar cycle, but are most common during the declining phase, such as in 2017 and 2018. And just to recap again, any signal that passes through the auroral zone, that's the north or south pole, can cause problems if the K index is high. So paths like from the UK to Western Canada, VE7, or even W6 in California, W7 up there in Washington State, that can be severely affected if the K index is high. Now earlier I introduced the term D region or D layer and F layer, and this really shows you whereabouts they are in the grand scheme of things. And these regions, rather than layers, we generally define them as being the D, E and F region, with the D region being the lowest. As far as HF is concerned, we really think of the D region as an area of absorption, or a layer that causes absorption, especially on the lower frequencies. So this is why we don't hear much on perhaps medium wave or top band during the day, because any skywave signals get absorbed by the D region before they ever get to the E and the F region. So any skywave signals going up are absorbed before they can ever come back down again. At night, when the D region disappears, we start to hear signals on medium wave and top band as they're not being absorbed by the D region anymore, and they can now be reflected back off the E and the F region. So going up a little bit now to perhaps 100 kilometers, 95 to 150 kilometers, we find the E region, and this is the region that's mostly responsible for propagating signals in the lower HF spectrum, notably 1.8 to 7 megahertz. It's there during the day, it's still there at night, but it's much, much weaker. It's very, very weak indeed, but it's still there. Up even further still, we find the F region, which is used to propagate signals in the HF spectrum between 1.8 and 30 megahertz. So if you're hearing a station from maybe the USA on 10 meters, chances are it's being propagated via this F region. During the day it splits into the F1 and F2 regions, and at night it combines into a single F region. Now, there is another way of measuring the level of ionization in our ionosphere, and that's to look at something called the critical frequency. It's sometimes shown as FOF2. Now, to do this, we fire a signal straight up into the ionosphere, vertically up, and we see if it comes back down again. Does it actually get refracted or reflected back to the Earth? And as you can see from this example on the slide, a 5 megahertz signal is being reflected back down from the F2 layer. It comes straight back down to the Earth. Whereas a 10 megahertz signal is going straight up through the F2 layer, straight out into space. So if we were to ask, well, what is the critical frequency here? Well, it's got to be somewhere between 5 megahertz and 10 megahertz. There has to be a point where the signal is not going to be returned back to Earth. And what we find is that at night and at positions in the lowest part of the sunspot cycle, at sunspot minimum, this critical frequency is a lot lower than it is during the day and at sunspot maximum. And we can use something called a digisonde or ionosonde to actually automatically do this measurement for us, and the figures are available on the internet. So again, we can very quickly just look at the critical frequency for our part of the world at that particular time of day, and from that we can actually work out what conditions are going to be like on longer paths. Now, on the previous slide we showed a signal going straight up and straight down, so-called NVIS or near vertical incident skywave radiation. And this is the kind of propagation we'll use on perhaps 80 meters or 40 meters when we want to talk to people around the UK. The signals are going to go up at quite a high angle and then come back straight back down again to Earth. So for that we need to have the critical frequency high enough that it will actually return the signals. And this is why we sometimes find that 40 meters, especially at sunspot minimum, is too high for this NVIS radiation, and we may need to go down to 80 meters to get a signal back to Earth. But not all signals are going to be sent up at high angles. So how do we talk to people perhaps in the US or Australia or some other part of the world? Well, then the signals are going to go off from our station at a much, much lower angle. And as you can see here, as we increase altitude and enter the ionosphere, we have a decreasing refractive index with the ions that are up there. So waves that are sent at more oblique angles slowly getting refracted back until they actually return back to Earth. And you can see here we get a point where we get total internal reflection and the signals get returned back to Earth. This is exactly how we get signals perhaps on 20 meters or 14 megahertz or 10 meters, 28 megahertz from the USA. In fact, they probably undergo 2 hops from the States. So we're getting a hop from the ionosphere and another bounce from the sea or the ground, then back up to the ionosphere and back down again. And so we need multiple hops to get signals right the way around the Earth. Now, as I said, you can measure the critical frequency using something called a digisonde, and we're lucky enough to have one in the UK at the Rutherford Appleton Laboratory. And this, as I said, fires signals straight up into the ionosphere and measures them coming back down again, and it sweeps right from the bottom of the spectrum right the way up to about, I think, 15 megahertz. And from this we then get a graph, and this is an example of one of the graphs on here. What we can see here is that it tells us that the critical frequency, that is the frequency that signals that are going to just be reflected back to the Earth, is 4.625 megahertz. That's the critical frequency for the F2 layer. There's also a critical frequency for the E layer as well, and that's shown on here as 2.91 megahertz. If you see one of these plots, it gives you this information on the left-hand side, or you can actually read it off the graph itself. From this, we can then deduce something else. We can deduce, well, what would be the maximum usable frequency over a longer path? And this suggests that over a 100-kilometer path, about 62 miles, that we could use 5.2 megahertz, or over a 3,000 kilometer path we could be using 14.9 megahertz. So again, what it's doing is actually working out the maximum usable frequency over a long distance from the critical frequency. It's not actually measuring that distance, it's actually suggesting, well, given this information, we can deduce that the maximum usable frequency over this path would be X or Y. So they're very useful things, digisondes, and as I said, you can find out more information at ukssdc.ac.uk, as it says on the slide. Now earlier we spoke briefly about the D layer, and that's this region at about 60 to 90 kilometers that's mainly responsible for absorbing and attenuating signals on the lower bands, although it can be used to reflect signals at VLF. So if we're looking at 160 meters, 80 meters, 40 meters, it's this D layer that's actually absorbing the signals as they go up. So on 80 meters you may find a condition where you can talk to somebody in the UK in the morning, but around about lunchtime you find they're not as strong as they were, and that's probably due to this D layer absorption, which is obviously affected by the sun. So in the summer, or around about lunchtime in daylight, then D layer absorption is going to be at a maximum, and conditions aren't going to be terribly good on perhaps 80 meters, 3.5 megahertz. But the actual level of absorption is going to be dependent upon the frequency you're using, the time of day or year, and also the solar or geomagnetic levels. Now, this horrible looking equation actually tells us what the absorption level in dB is going to be like in that D layer. Now, don't worry about it. All you need to know is that the lower the frequency, the more the absorption. It actually goes as the inverse square of the frequency. So you're going to have more absorption at 3.5 megahertz than you are at 7, and even less absorption at 20 meters. So by the time you get 20 meters and above, D layer absorption doesn't really play too much of a part. But it does mean that on 80 meters especially, and 160 meters, that's 1.8 megahertz, absorption is a major factor. So during the day or at times of high sunspot activity, they're not going to be terribly good bands to work DX on. So what we can do now is put it all together and see what we end up with. So this first graph is a graph of the lowest usable frequency that can be used at any time in that 24-hour period. And it's going to be related to that D layer. So as you can see, we can use quite a low frequency until the sun comes up. Then the lowest usable frequency will increase as the sun's intensity on the D layer increases. And then as the sun goes down, the lowest usable frequency drops again. But at the same time, the sun's going to come up, it's going to illuminate the F layer of the ionosphere, and the maximum usable frequency that you can use over a given path is going to increase. So we end up with a situation where we want to really work in this channel between the maximum usable frequency and the lowest usable frequency. As you can see, once the sun comes up here at 6 o'clock, the MUF rises quite quickly, and as does the lowest usable frequency. And what we need to really try and do is find a frequency that is somewhere between the MUF and the LUF, and we call it the FOT, or frequency of optimum transmission. And it's this frequency that we probably recommend you to use on any given path across the world. And as you can see, it increases when the sun comes up, and then as the sun goes down, it decreases. So you have to change the frequency that you want to use to work somebody in any given part of the world. Now, that's a lot to take in, and the level of ionization and the maximum usable frequency that you can use across any part of the world is going to be quite complex, because it depends where your signals are actually heading, and also where is the sun? Is it in the northern hemisphere or the southern hemisphere? That is it in summer in the northern hemisphere, or is it winter in the northern hemisphere? What time of day is it? Where are we in the sunspot cycle? There are an awful lot of factors to take into account. So the best thing to do is use a computer program or the charts in RADCOM to actually work out the best band to use for your particular path that you want for any particular time of day or month. Now, one of the ways of doing this is to use something called VOACAP. And there's actually an online program that you can freely use called VOACAP Online. Just Google VOACAP and you'll find it. So what you can do is you can put in your details, and in this case we're in the UK, so it will give you a map, a hotspot map if you like, of the probability of being able to work these various parts of the world on particular band. So this one was actually calculated for 14.1 megahertz, and you can see at this particular time of day, on this particular time of year, we've got quite good probability of being able to work maybe down into the Atlantic and into the Caribbean, but virtually no chance of being able to work Australia on short path anyway on 14.1 megahertz. So VOACAP Online is a very, very good tool for working out what you can work and when. And so if you know you want to talk to somebody in, say, Brazil, you can actually use VOACAP Online to work out the best band and the best time to actually make your contact. VOACAP Online will also let you do point-to-point calculations. So in this case, what we've done is we put one pointer on the UK, we put the other marker on New York, and it's given us a chart like this. Now you can see this lowest usable frequency and maximum usable frequency actually in action. As you can see, as the day goes on and the sun comes up around about 7 o'clock in the morning, the lowest usable frequency increases, which is due to this D-layer absorption. But at the same time, the maximum usable frequency increases as the sun is illuminating the F layer around the Earth. And so we end up with this channel, if you like, of frequencies that we need to work. So for example, if you wanted to work New York at around about 4 o'clock on this particular day, it's suggesting that we need to actually look at about 18 megahertz to make the contact. There'd be absolutely no point in trying to use 7 megahertz. That's way too low and there's too much absorption for that to happen. But then again, it'd be pointless to try and use 10 meters because the maximum usable frequency is only going to be about 21 megahertz or thereabouts. So again, VOACAP Online, very, very good if you're trying to do point-to-point calculations to work out what band do I need to be on at this particular time of day or this particular time of year to actually make the contact. VOACAP Online has another little trick up its sleeve. It can produce a chart like this one. Again, this is for New York, but it's showing us a 24-hour chart of all the bands and the probability of being able to make that contact on that particular path at any 1 hour in the 24-hour period and the best band to work on. So we can see on the right-hand side of the chart that that's nighttime, and we're not really going to be able to make that contact for on anything higher than about 30 meters, 10 megahertz. But on the left-hand side of the chart, which is daytime, we see that we can actually work right the way up to perhaps 15 meters, 21 megahertz, maybe even a little bit higher. So again, it's a very, very good way of seeing what band at what time you could actually make a particular contact, and also the probability of being able to make that contact. And that's actually what we're talking about. We're talking about probabilities. I can't say to you that on this particular day you will definitely make a contact, but I could say you maybe have an 80 to 100% probability of being able to make that contact, or a less than 20% probability of being able to make that contact if, say, you were trying to do it on, I don't know, 10 meters at night. Probably have a 0 probability of being able to make that contact. But propagation predictions are really all about probabilities and giving you the most accurate probability that we can, given the information we have, although people do always get surprises. So that was VOACAP Online. If you want to have your own PC program to make these calculations and actually come up with similar charts, there is a lovely program called VOAProp that uses the same engine as VOACAP to actually produce these charts on your own computer. It was written by Julian Moss, G4ILO, who is now sadly silent key. He's no longer with us, but VOAProp is still available and you can download it and run it on your computer. The first thing you need to do is download VOACAP and install that on your computer. Then you can install VOAProp on top of that. All the instructions are on VOAProp, so just Google VOAProp and you should be able to find out how to download it, install it and use it. Very, very simple program to use. You just need to tell it what month it is, what the sunspot number is, but it can do that automatically, and then it will show you a graph or a chart of what you can work at what particular time. Now VOAProp can also do point-to-point calculations. Here's two of them, from my QTH to the Bahamas and my QTH to South Africa, and you see you get totally different graphs. The one for the Bahamas shows you that at night you might need to use 7 megahertz to be able to make the contact, and they're likely to be about S4, S6. During the day, you might be able to use up to 20 meters or maybe even 17 meters, 18 megahertz, and they're likely to be about S1 to S3. But then again, if we look at the same path in October for the path from the UK to South Africa, you'll see that during the day there's probably little chance of making the contact whatsoever, and you're going to have to wait until the late afternoon or evening, and from that point onwards you're going to be using 18 megahertz and then sliding down to 20, maybe 30 meters, then 10 megahertz, and maybe ending up on 40 meters. So again, VOACAP lets you work out pretty much precisely what band you need to use at any particular time to make that contact. Now, if you're not particularly interested in computers, don't worry, because RADCOM has some tables that are produced by Gwyn G4FKH every single month, and that will give you a probability figure of 0 to 9 on whether you'll be able to work a station in any part of the world at any particular hour of that month. So they're available in RADCOM every month or on the RSGB website. So in conclusion then, let's put it all together and just have a look at what we've discussed. So generally, high solar flux levels and more sunspots are generally good for HF conditions, whereas solar flares, coronal mass ejections that give us high K and A indices are generally bad. These result in high absorption and lower ionization of the F region, so are less likely to be able to give you or support long distance communication, especially if it's over the polar regions. So if you want to know a real-time indication of what bands you should be concentrating on, then Solar Ham will give you the solar flux indices, the K index, the solar wind speed, and the direction of the interplanetary magnetic field, the BZ, which will give you a real-time indication of what bands you might want to concentrate on. The Chiltern ionogram using the Chiltern Digisonde at the Rutherford Apson Laboratory will also tell you the critical frequency at any particular point. So that's a real-time indication. Or if you're not too bothered about precisely what's going on at the moment, you can use something like VOACAP or VOAPROP to get an estimate of what you'll be able to work at what time and where. Now, very briefly, spring, autumn, winter are generally better times than HF than summer, as the ionosphere is cooler, denser, and the maximum usable frequencies are higher during the day in spring, autumn and winter. Now that may sound odd. You would think that because the summer there's more sun, maximum usable frequencies might be higher in the summer, but generally the ionospheric composition, the chemical composition, is different in winter than it is in summer. So we find that the MUFs in summer during the day are lower, but we find that the nighttime maximum usable frequencies are higher in the summer. So just to recap then, so that's maximum usable frequencies are generally higher in winter than they are in summer during the day, but the maximum usable frequencies at night are generally higher in summer than in winter. So it may be in the winter that 20 meters closes completely at sunset in winter, as I said, but you may find that 20 meters will support worldwide communication in the middle of summer at night time. So don't just think, well, it's night time, the bands are closed, there's nothing worth listening to. Far from it. You may find in the summer that 20 meters is still open. Now obviously we were talking about the northern hemisphere there, so the opposite is true in the southern hemisphere. So this is why it's quite complex. There's an awful lot going on. Now generally spring and autumn around the equinoxes, that's March 21st or thereabouts, September 21st, there we've got equal illumination on both hemispheres, so they're pretty good times for trans-equatorial contacts. So if you're trying to work South Africa, either March or September can be quite good months for that. Or if you want to work, say, across the equator and down into South America, again, spring and autumn can be quite good for that. In fact, autumn is usually quite a good time for HF, and it's very good for working the US as well on the higher bands. And to recap then, as the sun gets higher during the day, D-layer absorption can grow, but the maximum usable frequency rises at the same time. So if you're trying to work a particular path, follow the maximum usable frequency up during the day and then back down again as the sun sets at night. So during the day you're going to be using 20 meters, 15 meters, 12 meters or upwards, but at night time as the sun sets, then you're going to be dropping down to be using maybe 10 megahertz, 30 meters, 7 megahertz, 40 meters, or even 80 meters, 3.5 megahertz. If you want to know what to work and when, use the RADCOM prediction tables. Or if you don't want to do that, you can then use the VOACAP online facility. Just Google VOACAP and you'll, I think it's voacap.com, and you can actually work out your own charts for any particular path. If you want your own computer program for a PC, then as we mentioned, VOAPROP, HAMCAP, a paid for one is ACE-HF, and another good program that's getting a little bit old now is W6EL Prop, but it's still worth having and worth playing with. Also, I maintain UK monthly propagation prediction charts from the UK, as I said, at g0kya.blogspot.com. So if you go to g0kya.blogspot.com, follow the link on the right hand side, and you'll find a monthly chart that will let you select a band and an hour, and it will show you where you're likely to work. So you can very quickly compare different bands at different times, or you can compare different times for a particular location. What would be the best best time to work a specific location on a particular band? Well, that's it for this presentation. I hope that you've taken something away from it, and this is a bit of a trial really, and we're hoping to put some others together. But in the meantime then, thanks very much for watching this. This is Steve Nichols, G0KYA of the RSGB Propagation Studies Committee, wishing you 7-3 and good DX.